Welcome to another video in the series about the C7000 compiler. This video introduces scalable vectors. My name is George Mock and I'm your guide. Why have scalable vectors at all? Well, the C7000 series of DSPs have different vector widths. They're not all the same. Some examples. C504, the vector width is 256 bits. C7100, 512 bits. And so on. There's more DSPs to come, and the vector widths will be different among them. Now, what is true among all of these DSPs is that it's most efficient to work at the vector width of the DSP. Well, the way we solve this problem is the compiler supplies a method to create scalable vectors. They scale as the vector width changes, scalable vectors that are automatically the ideal length for that given DSP. Before getting into scalable vectors, I want to make a brief detour and describe one C++ language feature, and it's called C++ type traits. If you've heard of these before, you can skip this part of the video. If you've never heard of them before, you're not going to really learn the entire story of type traits in a single slide. I'm just going to give you sort of a flavor of what type traits can do. So it is a standard header file. That's the name of it, type traits. And what's it for? It allows you to query for some template. Here's a function template. The type is not specified at the time that you write the code. That specification happens when the code is built, and you can basically ask, well, what is the type that I have? Okay, so for this instantiation of the function, it's going to print integer. For this instantiation of the function, it's going to print floating point number. And these lines that I've highlighted, this bit that I've highlighted, is the type traits being actually used, and that's what I want you to gather from this portion of the video. The heart of this video is this example, which I'm sure is mostly confusing right now. That's fine. What I'm going to do at this point is a high-level overview of the example, and then we're going to walk through it one small piece at a time and then put it back together. Okay? So sum by scalable, what it does is, starting at this base address, of a bunch of integers, it's going to add up length integers together and return that value. In a previous video, I did this with vectors of length 4, and I called it sum by 4 because we were working through it 4 ints at a time, 4 ints in each vector. This one, we're using scalable vectors. Okay, so the first part is some setup, probably the most confusing part, and that's probably where we're going to spend most of the time. The next part is we're walking through actually, a vector's worth at a time, adding up values. This next part, there's a few values left over, and I will explain that. There's a few values left over to add in. And then this last part, we're walking through the vector horizontally, if you will, adding up everything into a single scalar value that gets returned. The first line of the example includes the header file C7x scalable.h. This is a header file you have to include if you're going to use any of the scalable vector features. One of the things unusual about this header file is that it only supports C++. It uses C++ features in its implementation, therefore it can only appear inside a C++ source file. It defines scalable types such as int_vec and scalable utilities such as element count of, all in the C7x namespace. I always write it this way. I explicitly specify the namespace that these guys are coming from every time they appear. That's not the only way you can do it. There are also using declarations, using directives, things like this, and I'm not going to cover those. I always am explicit about it. Finally, here are the scalable vector types. In this case, in this example, int_vec is the one we're using, and you see it appears 4 times in this code. This defines a vector of int, how many integers are in this guy, whatever comes to the ideal length for this DSP. All right, so what this first line does is it creates a vector variable sum SV. The SV stands for scalable vector. And this is what it looks like to initialize all the integers in it to 0. Okay. The second line creates a pointer to a scalable vector and initializes it to the argument that was passed to the function. PTR is the name of that argument. We cast it, assign it. In addition to the type intvec, many other types are supported, and here are some examples here: charvec, uintvec, and so on. The last part of the setup code computes the vector length. So we create a variable named vector length, and then we use the utility in the C7X namespace from the C7X scalable header file, element count of. This is its input, and then in a type traits way we access the value field, assign it to this constant. Okay. What are the typical values you see here? 16 and 8. Usually 16 or 8 integers in the ideal length vector for the DSP. The setup code is complete. Next up is the addition. This code iterates length divided by vec length times to some values from pointer SV into sum SV. So this addition is a vector operation that I've presented before. Okay. What's interesting about it is that just looking at the code, we don't immediately know, well, how many integers are being added together with this addition. But we do know that whatever that is, it is using the maximum capability of the DSP to do this addition. All right, so you're basically maximizing the parallelism that's available in terms of vector addition. Recall that integer divide in C always drops the fractional part. Therefore, this expression, length divided by vec length, is always going to yield an integer value. And vector length, like we've already talked about, scales with the DSP vector width. Now the main loop is over. It is time to add in the remaining values. And this comment does a good summary of talking about what happens here. Okay, add in the last length mod veclen values from pointer SV. Okay, so in a previous video titled Vector Comparison and Predication, I gave an example of this where it used mask bool 4 and length mod 4. The thing was all locked down to a vector of length 4. And then in a subsequent video titled Vector Predicate Representation, I showed how to use vpred instead of bool 4, which is what's happening here. And the reason we're using vpred here is because there is no intrinsic similar to mask int that returns a C7X bool vec. Okay, so we use vpred instead. Okay, so what's happening is instead of length mod 4, it's length mod whatever the vector length is in this case. Now keep in mind that veclen is a variable when we're looking at the code, but at compile time it's constant. Okay, and then that puts a mask into the variable MVP. That's an input to the select intrinsic, which is selecting between either values from pointer SV, the input passed into the function, or this is an int vec of all zeros. One or the other of those is what's getting added into sum SV. Select is overloaded. It can take a Boolean vector here or vpred. The last part is computing the scalar sum. This is all ordinary C code, sort of thing that we've all seen many times. The only thing unusual worth pointing out is this .s sub I syntax. That's how you access the ith element of the sum SV vector. I actually introduced that syntax in the first video on vectors. I've completed going through the parts of the example, so now let's look at the entire thing as promised. So these are the arguments into the function sum by scalable. Here's the setup code using int_vec where it needs to, element count of. Here we are going through the loop to sum values from here into a sum SV, working a vector's worth at a time. And remember, this vector is the perfect length for the DSP we're running it on. Then we add in the last little bit, and then we sum it all up into a single scalar and return that scalar. Now I extend the same example another way as a function template, which looks like this. For those of you who've never seen a template in C++ before, I recommend you not start with this example. It's a bit too complex for that. If that's you and you really want to understand what's happening here, I recommend you stop, go work through a tutorial on C++ templates, and then come back. So this is what it looks like to write a template. And there's the type T. That's what's going to be returned by this function sum by scalable template. That's the type of the values being passed in, and this is how many there are. So really what's happening is the type int is changed to the type T, and that is deduced when the function is called. T could be, say, float or short. Things like that. Since it could be any of those types, you cannot use the int_vec type. That is locked down to vectors of integer. So what you do instead is you use this utility from C7x scalable.h called make full vector, and it looks like this to do it, to create this type tvec, and then everywhere we were using int_vec before, now it's tvec. Okay. Now this is not all the changes that need to be made in the function, but this is most of them. For the rest of the changes, I leave that as an exercise to the viewer. There are yet other scalable vector types available in C7x scalable.h. If you would like to create a vector that is exactly 1/2 the size of the best vector for the DSP you're on, you would use type names such as char hvec. H is for half, short hvec, and hvec, and so on. If you need vector types that are exactly 1/4 the best vector size for your DSP, the type names are char qvec, where the q is for quarter, short qvec, int qvec, and so on. I want to close this video by giving you 2 references. The first one is to this web address here. That's the home page for the C7000 compiler. I think that's a bit too much to type in, so I recommend that you search for C7000 compiler. Every time I've done this search with different search engines, I've gotten this result in the first or second result. Here's where you can download the compiler, access the manual, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including the C7000 compiler. If that question is related to the compiler or related tools, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.